Steve, S-T-E-V-E, Buckingham, B-U-C-K-I-N-G-H-A-M.
We can hear everything everybody says.
So you're ready to go?
Yes, Pete. Go ahead.
Okay. I thought I'd discuss this a little bit of why this location was chosen as the Hanford location was chosen for the Manhattan District. DuPont was asked to design and build this facility, but DuPont was accused of war profiteering during World War I, and so DuPont was very reluctant to take this job on. But the Department of the Army Corps of Engineers kind of twisted their arm a little bit, and they finally convinced DuPont to take on the job of designing this facility. They said they would do it for cost plus $1. And because they were able to complete the job under the time estimate and under the cost estimate that the Corps Army Corps of Engineers had calculated, I understand DuPont only received 80 cents for their effort here. But Colonel Groves, the head of the Manhattan District, asked Colonel Mathias to find a location to build this new facility, something that had never been done before. And Mathias had essentially 4 requirements. One, it had to be someplace out west because they didn't want the 2 plants, the isotope separation plant and this plant to build this new material anywhere near each other. So it had to be out west somewhere. It had to be in a somewhat of a remote area because this was new technology. Had no idea what was really going to happen with it. 3, it had to have a lot of water available because this process generated a lot of heat, and they had to have some way of dumping this heat. And 4, there had to be a lot of electricity available because for pumps and so forth. Well, Mathias looked at several places out west. He looked down around Las Vegas. He looked in eastern Oregon. He looked down around Idaho.
Start with his name again.
Name again?
No, it's the same tape. So they're just going to find you in a different, quieter place.
Okay.
Yes, that's true. That's why we
Okay.
Okay, yes,
Okay, you want to tell us the story?
Okay, I thought I'd mention a little bit of why Hanford was chosen as the location for this facility.
look right at her.
And DuPont was asked to design and build a facility to make this new material that was later called plutonium that Glenn Seaborg had found out at the University of California. General Groves asked Colonel Mathias to find a location to build this facility. And he had 4 requirements. One, it had to be someplace out west because Oak Ridge was where the isotope separation was going to take place, and they didn't want the 2 facilities anywhere near each other. 2, they needed to be in a remote area because this was something new. They didn't know what was going to happen. So they didn't want to be near any population centers whatsoever. 3, it had to have a lot of water available because this facility created a lot of heat. They had to have some way of dumping that heat. And 4, there had to be a lot of electricity available to pump the water. Well, Colonel Mathias looked at several places around the west here. He looked down around Las Vegas. At that time, Las Vegas was just a railroad stop. Wasn't the big metropolitan it is today. He looked at eastern Oregon. I think he looked at some place down in southern Idaho. But this area at the Horn, what we call the Horn of the Columbia River, had all the requirements. It was out west. It was a remote area. The nearest city of any size was Spokane, 120 miles away. They had the Columbia River, one of the purest, most pristine rivers in the world. And there was a lot of electricity available because the government had just finished building Grand Coulee and Bonneville Dam, and we were halfway between the 2. So there was lots of electricity available. So this is why Hanford was chosen as the location. There was only about, 2,000, 2,500 people living here. So it was just small communities, really. Small town of White Bluffs, probably 500, 600 people. Hanford, about the same. Richland, about the same. And then the farmers that were living around here. Now, the Corps of Engineers asked DuPont to design and build this facility, but DuPont didn't want to have anything to do with it because during World War I, they were accused of war profiteering. But I think the engineers, Corps of Engineers, twisted their arm a little bit, and they finally agreed to do it. They said they would do it for cost plus $1. Well, because DuPont was able to design and do this, build this facility under the cost estimate and under the time estimate, I understand they only received 80 cents for their effort, but that was a very patriotic thing to do, and they did get a lot of knowledge building this facility. Well, they opened, the people who were living here were given 30 days to get off their land because it was, and they didn't know exactly what was going on, but they knew it was an important, they were told it was an important war effort. And the rumors of what was going on here were rife. Some of them are really quite hilarious. One of them that was a camp that service women who got into a family way could come here to have their babies. Another one is they were making campaign buttons for Franklin Roosevelt's presidential campaign. So all sorts of interesting stories about what was going on. Now, DuPont, they had to recruit people, and the War Manpower Board dictated where you could recruit because of wartime. And you just couldn't go over to the coast, say, and recruit people from the shipyards or the Boeing over there. So a lot of recruitment was done down south because the South wasn't highly industrialized in the 40s. That's why so many Southerners live here, and they were given a railroad ticket, and I have to always kind of laugh because the trains came through the Pasco where the railroad station was located about 2 o'clock in the morning. And I'm sure if it had come by during the daylight hours, they wouldn't have bothered to get off the train and look at this desert, because the recruiting posters were really funny. Come to the evergreen state of Washington, sparkling rivers, snow-capped peaks, wonderful fishing and hunting. What did they come to? They come to a desert. The trains were met. They were given a place to sleep the rest of the night. In the morning, they went through employment, put on a bus, and driven the 40, 50 some odd miles from Pasco out to this huge construction camp out here at the old Hanford town site. At the peak of employment, there were 55,000 people. It was the 4th largest city in the state of Washington. People lived in barracks, dormitories. The women's barracks was on one side of the camp, surrounded by a barbed wire fence. And because they were recruiting, manpower was so short, they were recruiting girls right out of high school to come here to work as waitresses, secretaries, clerks, anything, So they decided they needed to do something to kind of protect these girls. So they hired a Mrs. Maris. She was Dean of Women at Oregon State College. And she came up here and established what she called the women's division. And she did such things as organize all sorts of clubs to make life a little bit more human, civilized here for these young girls. The girls' barracks, the women's barracks was surrounded by barbed wire fence to keep them in, of course.
Okay, hang on a second.
We got somebody talking out there. Could you
Mrs. Maris and the
and the Women's Society, Women's Affairs. She was in charge of Women's Affairs.
Attorney.
Mrs. Maris was in charge of Women's Affairs, and she organized a lot of things like sororities, scout clubs, all sorts of clubs and that type of organization. She'd organize shopping trips for these women, because here they were living out here in the middle of nowhere, and the nearest store of any reasonable thing was 80 miles away, or things like that. So it made life a little bit more tolerable. And they did a lot to try to make life more tolerable out here. They built an auditorium. It held 5,000 people. It took 7 days to build this auditorium. Big name bands came here and played. Jimmy Dorsey played here. Ted Weems played here. Kay Kaiser played here, and several more. They built a big tavern. At that time, the only thing you could drink in the state of Washington was 3.2 beer, 3.2% alcohol. They opened a brewery over in Walla Walla to make beer for the Hanford Project. Pioneer beer wasn't all that great, but it was beer. At that time, also in the state of Washington, you had to sit down to drink. You couldn't pick your glass up and move it to another table. A waitress or a waiter had to do that. So people would get off work. They would rush to the tavern, claim chairs, and then auction their chair off to the highest bidder. Somebody was always trying to make a buck somehow or other. Many people who came here had never received a paycheck before. Their boardroom was taken out of their paycheck, and they left here with thousands of dollars of uncashed paychecks. Everything was paid for, essentially, so it was an interesting life. But now I'm going to talk a little bit about B plant. Now, you've covered the B reactor, where the fuel was irradiated. Now, the fuel was it was uranium metal. It was approximately 8 inches long and about 1 inch in diameter, and it was canned in an aluminum can. Now, after the fuel was pushed out of the reactor, it stayed in the basin for up to 30, 90 days, depending, to allow short-lived fission products to decay away. It was then put into what we call a cast car. Now, this was essentially a large tank of water. There were 3 divisions in the tank, and the fuel was placed in those. It was on a railroad car, a flat car, and then moved by rail up to T plant, where the chemical separation took place. Now, because it was usually moved at night, because even with the water and the lead shielding around the cast cart, it was extremely radioactive, and they'd have to barricade the roadways as the train passed, because just from the radiation and there'd be 3 or 4 blank cars between the cast cart and the cast car and the locomotive, so the locomotive crew would not get irradiated. It arrived up at T plant, which was our first separation plant. It was moved in through a railroad cut into the T plant building. Now, T plant itself was a marvel of design. It was approximately 800 feet long. It's about 80 feet tall, about 75 feet long. And the cells in T plant, where the separation process took place, are about 9 feet thick of reinforced high-density concrete. The fuel was pulled out of the cast cart and put into a storage cell, and then later it was moved into a dissolver where the aluminum jacket was removed. And then the uranium that was left was what they called active metal, was then dissolved using nitric acid. Now, back in the 40s, when you dissolve any metal with nitric acid, you release a lot of brown fumes. So these brown fumes would go out the stack, and you could always tell when we were dissolving, because there would be a brown haze laying around on the horizon. After the fuel was dissolved, we went into a feed tank, and then batch-wise it was moved into what we call the precipitation tank. And in the precipitation tank, we'd have to adjust, add some chemicals to adjust what we call the valence state of the material. Then we'd add, now because when you irradiate the uranium in the reactor, for every ton of uranium that went into the reactor, we would only generate around 1/2 pound of plutonium. So it's not much plutonium you're making for a great huge volume of uranium. So we had to add another chemical to the to this dissolver solution to give enough bulk so we could precipitate the plutonium. So we added bismuth, which has similar chemical characteristics as the plutonium. Glenn Seaborg developed all this process in his laboratory using just a few atoms of plutonium, which to me was amazing. And because we had such a very little time to do all this, they decided they would go directly to the design and the operation of T-plant without a scale-up. It went to laboratory to full-scale production, a scale-up of about 1 to 1 billion, which was an amazing gamble that paid off. Now, so we'd add the bismuth, and then we'd add phosphoric acid to precipitate bismuth as what we bismuth phosphate, and that's where we get the name, the bismuth phosphate process. The bismuth would precipitate and would carry down with it the plutonium. Then the material was, from the precipitating tank, it was then jetted into a centrifuge. Now this was you think of your washing machine that uses a centrifuge to remove the water, but these were big centrifuges. They were about 40 inches in diameter. They were called a bird centrifuge. And they would jet the material through the centrifuge. The precipitate would collect on the walls of the centrifuge, and the thing that always kind of amused me and amazed me was they had microphones down in these hot cells, and the operators could sit there and could tell from just the sound how the centrifugation was going. They could tell when it was finished, and then they would use what we call a plow, which was just kind of a scoop that would go in. They ran hydraulically from the operating gallery. They would kind of plow the plutonium off and flush the plutonium out of the centrifuge. This was a pretty tricky process because it didn't come out all that easily. They'd have to start the centrifuge rotating very slowly, then stop it to kind of get a washing solution to get it off. Very clever, though. Well, this was what we call the first separation process. The plutonium was removed from the uranium. The uranium was then sent out to our tank farms, and it was a valuable resource. So even way back in the very beginning, we had ideas of how to recover that uranium, but because of the time constraint, we had to get this done, so we went with the process that we had available. The plutonium was then redissolved, and we went through another strike. This time we changed the valence of the plutonium so the plutonium would not precipitate. It would stay in the supernatant liquor. So we would go through 2 of these strikes, and every time we would go through one of these processes, the plutonium would get more and more pure. And finally, after going through, about 10 or 12, so we'd rechange the valence state and precipitate some things and precipitate the plutonium and discard other stuff. But every time we'd go through one of these precipitation steps, we would get a more and more pure plutonium. And finally, down at the very end of the process, instead of using bismuth, we used lanthanum and precipitated it as lanthanum fluoride. Now, the reason we didn't use lanthanum early on is lanthanum is a rare earth and rather rare. It's rather expensive. So when we get down to a smaller volume, then we were able to precipitate it like this. Then the material was, we then had to metastasize. That's a chemical name you probably don't know. It's what we did is convert it from a lanthanum fluoride to a hydroxide by using potassium hydroxide on it. Then this material was, then we converted it to a peroxide using hydrogen peroxide, the same stuff you use as bleach. Women use it to bleach their hair, at least they used to. And then the plutonium peroxide was then dissolved in nitric acid, and we were able to concentrate it. The plutonium left Hanford as a paste, essentially. It was about like library paste. And the first plutonium, when it went out here to Los Alamos, it was carried by a second lieutenant in a briefcase, padlocked to his wrist. The only thing he could get on the daylight that left Portland heading for Los Angeles was an upper berth, so there he had to sleep in that upper berth, padlocked to this briefcase of plutonium all the way from Portland, Oregon down to Los Angeles, where he then turned it over to a captain from Los Angeles. But that was the first plutonium that left Hanford. Tea plant itself was a very interesting design characteristic because everything had to be done remotely. You could not, because of the higher levels of radiation, you couldn't ever get in and actually work with the stuff directly. So when they built the plant, they built what they call these hot cells. There are 40 hot cells in tea plant. They're covered with cover blocks that are about 7 to 9 feet thick, and they're stepped, so because radiation only goes in a straight line. And there was 4 blocks on top of each cell, and you had to take out the key block first, otherwise you would have trouble getting these interlocking cell blocks off. The tanks located were located down in the tank, in the cells, and there was a crane ran the whole length of the building. These crane operators were, boy, they were tricky. They were using optics to view what was going on in these process cells. And they could go in and, I swear, they could thread a needle with those cranes. There were 2 or 3 hooks on the crane and a couple of impact wrenches that then connected what we called jumpers. The jumpers would connect to the walls, to nozzles on the walls, which would then take it to the next cell. And all the instrumentation came through these jumpers, all the liquid transfers, all the electrical supply for the centrifuges, all the instruments, and excuse me, all these kind of things came in through these jumpers, and it was a marvelous design. The design is still pretty commonly used in almost all nuclear facilities all through the world now. It was designed, the design was developed here at Hanford, which we were very, very proud. Can
you talk about, explain the optics again, because of mirrored system.
Oh, the optics, because in the crane cab was located behind a parapet, and it was a lead-lined cab, so the crane operator could not view directly into what was going on in the cell. So we looked into a bomber sight that would look into a mirror that looked up and looked across and looked down, and they fixed it so it would reverse the image in the right way, so he wasn't looking at a mirror image all the time. And the crane was designed in such a way that he could move the optics and view what was going on in all these hot cells. And boy, my hats are off to those crane operators. They could just, you look at some of those hot cells and it actually looks like looking into a bowl of spaghetti, and they could go in and sort through all those jumpers and get the right jumper, the right piece of equipment, or whatever they needed to do. But most of the operation, of course, that was only when something failed or there was something wrong that the crane operator would call in there. Sampling was another big problem. We had several different types of samplers. One was called a doorstop. Doorstop was about 6 inches in diameter, I guess about this size, and about 8 inches tall. It was stainless steel. It had, I think there was some lead lining in there someplace too. I'm not right sure of how it was built. But that was where we'd put high-level samples. There was a little insert went into there, and then we used a plastic pipette. It was about 3 inches long, and it would contain maybe, some of them contained 1 milliliter of solution, some of them contained 0.5 milliliter of solution, and some of them contained 3 milliliters of solution. Because you didn't want to get a lot of these high-level samples over to the laboratory, because they were just giving too much, we give too much radiation to the lab workers. Then they used a contraption we called a trombone, which was just essentially a long tube that we put a syringe on the end of it, pulled the material out of the sampling cup into the, and then transferred into these door stops. Now the sample cups were about, they could have been 30, 40 feet above the tanks. So you can't, with vacuum, you can't pull a solution up that high. Vacuum will only go up about 40 feet. So we had to use what they call an airlift in there. We'd bleed a little bit of air. We'd turn on the jets that would start pulling the material from the tank up, and then we'd put an air jet in down below, and that would then help rise the solution from the tank up into this sample cup. And the sample cups were located between the cells, and it was, of course, covered with other blocks and lead and all kinds of stuff to keep everybody safe from some radiation, because that was a big issue way back even then, to protect people from radiation. And the laboratory was, actually we didn't have an awful lot of sophisticated laboratory equipment. We did most of our measurements by just measuring the alpha. The plutonium is an alpha emitter. And we did most of our measuring of what was in the different solutions from the process by measuring the alpha in these samples that we'd get over into the laboratory. It was new instrumentation. Everything here was new, of course, and it was new technology, brand new technology. The thing that always amazed me, back then, because of times and straits, we didn't have to go through a lot of red tape of getting approvals to do something. If something needed to be done, it was done, which was a marvelous attitude back then. It was very important to get this material made and out of here, because we knew it was going to end. We knew it was going to end the war, and it ended. Okay, I'd like to talk just a few minutes about DuPont and their safety attitude. Now, DuPont was a munitions maker. They made gunpowder. So they had a very high safety. When you work with gunpowder, that has to be safe. And they translated that attitude to Hanford. If safety really was #1 with DuPont. And I will say this, that we're actually safer at work than you were at your own home. It was just we used to kind of gripe about, another safety meeting, but those safety meetings were important because it did give us an attitude of how to operate, how to work safely. And of course, coming out of just a university attitude where you used to pipette with your mouth and never wear rubber gloves for handling with acids or caustics. It was a big cultural change to have to be able to use rubber bulbs or syringes to pipette, rubber gloves anytime you handled anything hazardous, any hazardous material, always wearing face shields. Big change, but it was well worth it because the safety record here was just really outstanding. There were really no deaths from the operation. There were some construction deaths, stuff like that, which probably couldn't be avoided. But as far as operations, this is a safe place to work. It's safer than your own bed, I suppose, if you want to put it that way. Now let's see, what is some of the other things I was thinking of.
Let me ask you this. Could you characterize the material that came out of B plant? What did you guys receive from B, not B plant, but B reactor?
From B reactor. The material that we got out of B reactor was what we called slugs.
I'm sorry. Look at her.
Okay.
Trying to talk to the guy who has
all right. The material we
I'm sorry, just start again.
all right.
If you quit laughing there, it's not funny. This is
Okay, very serious.
no, not very.
The material that we got out of the reactor, B reactor, was what we call a slug. It was uranium canned in an aluminum jacket or can, about 8 inches long, about roughly 1 inch in diameter. These were extremely radioactive, and they came up to the T plant in a cast cart, which I described a little bit earlier. That was the material that we had. That was our input into T plant. Chemically,
what were the properties? What were the properties?
It was just strictly metallurgy. Aluminum, just an aluminum, straight old aluminum can, and uranium metal. Then there was a bonding material that bonded the can to the uranium, and that was a rather tricky operation, as I understand. I'm not too familiar with the canning operation, but you'll get that tomorrow. The canning operation.
And you, just briefly, I just want to make that transition. Now you took this can, and what was the first thing you did?
First thing we did.
I'm sorry, because you got to look at
yeah.
her.
Okay.
Quit talking so that
the first thing we did when the material came into the plant is it was moved out of this container, this cast cart that brought it up into the plant. We put it into a storage cell, which was just a deep water, a tank full of water. And then from there, it went into a dissolver. The dissolver was just a tank, and that we could add. We added material into the tank to chemically remove the aluminum from the uranium. And this was a little bit of a problem area too, because that off gas was not particularly desirable. We had to handle it. It was moved out the ventilation stack. In the very early days, the ventilation stack was we did filter the gases, but not really highly filtered. Then when we began dissolving the uranium, after we got the jackets off and had to dissolve the uranium, we used nitric acid. And of course, when you dissolve metal with nitric acid, you give off a noxious fume called NOx. It's a brown fume, and this is stuff that environmentalists don't like nowadays because it damages the environment. We had no way of really recovering those NOx's at that time. Later on, we did put into facilities to filter these off gases. First we put in sand filters, and then later we used high efficiency particulate filters called HEPA filters to remove any particulate matter that were in these off gases. Go ahead.
You were going to tell us about some of the things that would convey to people how new this all was, some of the challenges, sometimes things didn't go right.
Yeah. We used to kind of laugh a little bit in the fact that these full-scale chemical separation processes were the world's largest pilot plants. I was what they called a process chemist, and Monday morning the process engineers and the process chemist and the operating people would get together to plan what was going on that week, and somebody always had some bright idea how to improve the process or screw it up, whichever way, whatever comes first. So sometimes they worked, and sometimes they didn't work, but it was we were really a pretty close society back then. We worked very closely together, we communicated well, and we got a lot accomplished. Everybody was open to new ideas, and even some kind of nutty ideas, because it was all new, brand new, new technology, just new instrumentation. It was something that had never been done before, and we had to do it. And I just marvel when I look at the engineering that went on, designing both the B reactor and the T plant, how they ever had enough foresight to design in some of the things they designed it. And when something didn't work, they designed in redundancy that allowed us to work around things that didn't work. My hats are off to those designers. It was a marvelous job of designing because it worked. We did it, and I'm proud we did it. Anything more?
Yeah, one quick story about some jury-rigged Rube Goldberg seat of the pants thing that you guys had to do that you're kind of proud of.
I've got to tell you about the Goldberg. When the sample came into the laboratory in the doorstop, of course it was extremely radioactive, and we had to find some way of removing the sample from the doorstop so we could make a dilution of it to analyze what was in it. And we came up with a contraption called the Goldberg. Is what this was, is we would place the doorstop, which was pretty heavy, it weighed about 20 pounds, on this kind of a platform that rotated. And then we would swing it around behind, and then in front of it there would be a real thick leaded glass shield with slots in it, and we had a device over here with that had a pipette on the end of it that went up over the wall, and we could poke it. Then it was such a way that we knew exactly where that hole in the doorstop was, so we could find the sample. Now remember, we're only working with half a milliliter at some times, which is not a very large sample. Be able to find that hole that held that sample, pull it up using a syringe into a pipette, and you'd have to then, with long tongs, you'd have to get in there with cotton swabs or cotton wipes to wipe that pipette down, to level it to the area, to the level, proper level, and then transferred it over into a dilution flask to dilute the sample. So then after you get it diluted, it was pretty well down to the point where we could work with it. Sometimes we had to continue to use lead bricks for shielding. We use an awful lot of lead bricks around in our laboratories and in the operating facilities. I think we must have had a corner on the lead market for a long time. Now lead is a hazardous material, unfortunately, but that was some of the things we did. Some of the other jury rig material that happened in the plants, I can't think of so much in the T plant as I can in some of the later separation plants that we built later on. But